Okay, welcome to deep learning course. So I actually tried to give you a quite big picture of this concept, big learning, and the materials that we are going to cover through this semester. So the first half of the class today is going to be mainly motivation and history of deep learning, and I'm going also to talk a little bit about course administration, marking, and so on. A part of course administration really depends on how many students are going to register in this course. Clearly, I didn't expect that many people to come to the first lecture. And I don't know how many of you are going to register for the course, how many of you are going to audit or just sit in the course. So I need to have an understanding, but I'm going to ask you toward the end of the lecture that how many of you are going to register in this course officially, and then based on that, we may want to change a little bit our course administration and marking scheme and so on. Okay, because it's a grad course, I don't have any TA, so I have to think if there are many people, I can't make any assignment. I can mark so many assignments because usually grad courses are much smaller than this. So we're going to decide. Okay, so deep learning, you can think of deep learning as different layers of computational units. So usually algorithms that are called deep learning have different layers of computational units. And the goal is that each layer extract or learn one level of abstraction. So if you want to, I'm standing here, and if you want to talk about me, you can explain to someone that there is a person here. Person is one level of abstraction. Standing, another level of abstraction. In front of this board, all of them, if you have a picture of me standing in front of this screen, when you're explaining this picture to someone, you're using different abstraction, a person, standing, screen. These are all abstraction because in real world, we don't have a screen. We have this one, and we have another screen, another screen, another screen. But we as intelligent agent or human being, we make an abstraction of all of these objects, which is called a screen. Or we make an abstraction of book of millions of objects that exist in the world. Book itself, the abstraction itself doesn't exist in the world. That's something that we created. So the claim is that deep network is a way to abstract, to create or to learn this abstraction in different levels. It's quite controversial. Many people do not believe that that's really what deep network does. Many people believe that deep network is just a very flexible function that we recently learned how to fit it to data without overfitting. Some people believe that deep network is really a huge memory, but it's a smooth memory. So it's a smooth lookup table that we memorize the whole internet, and then we claim that we have learned everything. So it's pretty controversial. There are people for it and against it, and at this moment, we don't want to get to this controversy, but later on, when we want to see why deep models work, we may want to know a little bit about this. But what I'm going to do first is to, as a motivation, show you some success stories. One of the reasons that many of you are here is that you have heard a lot about deep network and success stories of deep network everywhere. So I'm going to show you a little bit of this success stories and demos. It was just in the news a couple of days ago that some researchers made a new chess, game chess, that for the first time, this model learned itself how to play chess. We had chess from a long time ago. Plays very good using reinforcement learning, but it's usually through brute force. We have to have a tree at each stage. We have to know what are the other actions, other possible actions, and we have to program this. But this one doesn't need any of these steps. According to the claim, it's going to learn chess by itself in 72 hours. So it plays chess with someone else, or the model plays chess with itself and learn the rules and can play, at a very professional level. It was also in the news about a couple of months ago that some researchers with merge of reinforcement learning and deep learning was able to create models that can learn so far 20-something Atari games by itself. You don't tell them what the rules of this Atari game is, just it plays Atari and it learns. So I don't know, have you heard of Wordtoback or not, but it was quite interesting paper in 2013 and got lots of attention. So you can represent words using vectors. So basically, when you do machine learning, you need to do so even before Wordtoback, from the beginning of natural language processing. We used to do so, vector representations for any object, including text. We have to, the simplest thing that you can do, back of the word, we can assume that in, say, for example, you have 10 different documents. You just count the frequency of word in each document, and then you have a vector, okay? But Wordtoback use neural network. This neural network actually is not that deep, but use neural network and find a representation of words. So you basically project words in a new space, some vector space. But these vectors have pretty interesting properties. This is one example. If you take the vector which represents the word king, subtract the vector which represents man, and plus the vector which represents woman, it's equal to the vector which represents queen. So a king who is not a man but is a woman is queen. So very interesting relationship can be learned through these vectors. The distance between Paris and France is the same as the distance between Ottawa and Canada. And the same, the distance between CEO of a company and the name of the company, almost for all important companies, are almost the same. So you can infer even new knowledge and information from these vectors. It turned out that it works not only for words, but you can have a joint representation of words and pictures and images. So images can be represented as vectors, and words can be represented as vectors in the same space, such that, for example, if you have this image, the vector of this image, minus the vector which represents day, plus the vector which represents night, you're going to get one of these images. So if this picture hasn't been taken in day, but has been taken in night, look like something like this. Or if you have this object minus flying, so an airplane which doesn't fly, but sailing, it look like one of those ships. More interestingly, these examples, these cats in, say, for example, this cat in box. But cat minus box plus ball is one of those images, okay? There is a paper which shows how to generate captions for images. These captions have been generated automatically. This caption says a woman is throwing a frisbee in a park. The input of the model is just this picture, and the capture has been generated by the model. So the model basically explains what this image is. Okay. We have seen in the past that you can represent words in lower dimensional space such that close points, neighboring points, semantically are related. Like this one on the left. On the right, you can see that some vector representation of sentences have the same sort of properties. Close by sentences semantically are related. So you have a vector which represents a few days. There's another vector which represents in a few months, and you have a vector which represents a few months ago. They are pretty close, semantically close. So you can imagine all sorts of applications in natural language processing when you have this type of representations, and they are coming. Many companies now use, neural network is not just research. They're using neural network in all their applications. PayPal that you use every day, they use neural network to prevent fraud, for example. There are startup companies that use neural network, deep neural network, for X-ray and MRI pictures to diagnose different type of disease that people were not able to do that. This is an API that everyone can use, and you can see that very look-alike images has been detected correctly by deep network here. So the precision of object recognition has been increased significantly recently using deep network. The performance of speech recognition techniques has been increased by more than 20% recently using deep network. Most likely you have realized the difference between speech recognition in Google Now or Siri, for example, if you compare it with a speech recognition a couple of years ago. We used to call Rogers, and Rogers has automated speech recognition which tries to address different calls. And every time that I call Rogers, I get crazy, and I have to say agent until they contact me. Because really you say something and it, understands something completely different. Still, our voice recognition, University of Waterloo, you call and you say, I want to talk to Ali Ghodsi, and, connect you to James Stein. It's still, these are not, these are old variations of speech recognition using hidden Markov models only. New generation of speech recognition using deep network that you can see it in Google Now or in Siri using deep network. The performance is more than 20% better than before and really works. Okay. This is a quite interesting paper that's published 2014 in CVPR. You can recover voice from basically video of vibration. Okay, let me show you this video. Let me stop explaining that.
When sound hits an object, it causes that object to vibrate. The motion of this vibration creates a subtle visual signal that's usually invisible to the naked eye. In our work, we show how using only a video of the object and a suitable processing algorithm, we can extract these minute vibrations and partially recover the sounds that produce them. Even when we play the video in slow motion here, the vibrations caused by the music are so subtle that they move the plant's leaves by less than 100th of a pixel, making the plant appear still to the naked eye. But by combining and filtering all the time happening across the image that you see, you're able to recover this sound. In our next experiment, we recovered live human speech from high-speed video of a bag of chips lying on the ground. But to make things a little more challenging, this time we put the camera outside, behind a soundproof window. This is what a cell phone was able to record from inside, next to the bag of chips.
Mary had a little lamb whose fleece was white as snow, and everywhere that Mary went, that lamb was sure to go.
And this is what we were able to recover from high-speed video, filmed from outside, behind soundproof glass.
Mary had a little lamb whose fleece was white as snow, and everywhere that Mary went, that lamb was sure to go.
In this next experiment, we recover music from high-speed video of some earbuds plugged into a laptop computer. Then we take our recovered sound and use audio recognition software to automatically identify the song that was being played. Most frequencies of audible sound are much higher than the frame rates of standard video. So all of the results we've looked at so far were recovered from video captured by a high-speed camera, which can record thousands of frames per second. But in this next experiment, we show that by taking advantage of artifacts caused by the rolling shutter in most consumer cameras, we can sometimes actually recover sound at frequencies several times higher than the frame rate of our video, letting us recover audio from video captured on regular consumer cameras. Here we see a 60 frames per second video of a bag of candy captured on a regular consumer DSLR while our Mary Had a Little Lamb music played through a nearby loudspeaker. By using a variation of our technique on the rows of the recorded video, we are able to recover this audio, which includes frequencies more than 5 times higher than the frame rate of our camera.
Okay, so there are, after the course, you can look at this page. There are quite interesting demos of deep learning. Let me show you just one or two of them to you. Here, it's just right. This is a course in deep learning. And say, it can basically generate the text in different handwritten style that you can train it. You can train it for your handwritten style. My son was trying to make a model for a long time to type his homework. He's 13 years old, and make it like handwritten too, instead of writing. So it can be help in this. It can be used in this case. Okay, and let me show you another thing here. This is one of the first papers in deep learning by Jeffrey Hinton. It's a generative model. Interestingly, you can sample, it models a very complicated distribution that you can sample from that distribution, and you can generate new handwritten digits or new faces when you train it for face. For example, I would want to sample from 4, and the model can sample. Can you see there that these 4s are generated by the model? It's quite impressive that you're sampling from distribution, and basically this matrix you're sampling for each pixel, but you're sampling in a way that it looks like a real 4 that has been written by a person. You can sample from face. You have a collection of face of a person, and you sample from that distribution as if it's a picture of that person, but this picture hasn't been taken ever. It's just one sample of that distribution. So it's quite impressive that you can model this. Okay, so that was some success stories and demos of deep learning. What we are going to do in this course, there are these topics that we are going to cover. We are going to talk about feed-forward neural network and deep network, actually. Feed-forward neural network was the first maybe type of neural network in 1980s, quite popular. And now we are using the deep version of those neural networks now. It's quite tricky to optimize and to train these deep models, and we will talk about optimization for these models a little bit. Convolutional networks, many success stories that you hear these days are about convolutional networks, especially in object recognition. Convolutional networks also are old models by themselves, but we have deep models of convolutional network, or we have right computational power for convolutional networks that we didn't have in the past. So we'll talk about convolutional network. There are cases that your data is not IID, data is temporal, order of the data is important. You're talking about dynamical models, you're talking about modeling a language when the sequence of words is important. So when we want to model data that sequence is important, in those models, we have recurrent neural network, we have recursive neural network, and we will see those in this course. We're going to see autoencoders as well, which is a way for dimensionality reduction or for representing, for finding new representation of the data. And we'll see restricted Boltzmann machine and deep Boltzmann machine. That is basically the first deep model that was proposed in 2006. So I'm going to give you a detailed history of neural network in a few minutes. But a short story is that, at some point perceptron was invented, and perceptron leads to neural network, and neural network was popular for a while in 1980s. And then people lost their interest in neural network and for 20 years. And I remember the time that, in NIPS conference is a pretty, prominent conference in machine learning, they used to unofficially announce the most frequent words in rejected papers. And for 2 years in a row, the most frequent words And the title of rejected paper was Neural and Network. So it was not popular for a while. After support vector machine, it was not popular until 2006. 2006, Jeffrey Hinton published a paper in Science. That was the first model of deep network. Neural network that we're going to see in a few minutes was pretty difficult to train first, and then they realized that they can train it using backpropagation. But backpropagation, it was general belief that backpropagation can be used only for shallow networks if you have 1 or 2 layers, not more than that. If it's deep, you can't use backpropagation to train those models. In 2006, using restricted Boltzmann machine, Hinton showed how to train deep networks. Later on, it became clear that you can use backpropagation for deep network. Many of deep network models now don't use restricted Boltzmann machine. They use just backpropagation for training the model. So it became again popular due to this success that they had. Okay, we're going to put some emphasis on deep learning for natural language processing because that's my understanding of the area, that what you can do in speech recognition has been done already. Speech recognition basically somehow reached to its cap using deep network. Also about object recognition, an area that has, there is so much room, and there are many open questions and open area of research is natural language processing. So we're going to emphasize on natural language processing more. So in terms of marking, in this course, we are going to have a group project, group of up to 3, that is 50% of the course mark. We are going to have paper presentation and paper critics. For paper presentation, my plan is to teach like half of the course, about like 6 weeks of the course. I'm going to teach the basics of all of these techniques. And the rest of the course, the second part of the course, would be paper presentations by those who have registered in the course. So that will count 20% of your mark. For paper critics, I don't know how many of you have seen this wiki course note that I created a couple of years ago. So it's like it's based on Wikimedia. It's like Wikipedia, that collectively you can, create a text or change it. So we're going to use that for paper critic in different ways that I'm going to give you the detail later on. So one way is that when there is a presentation in class, say for example, person A is supposed to present a paper in class. Other people needs to write a summary of that paper and make contribution on that summary before the presentation. And also, there is another type of contribution that you are supposed to give your critic or summary of a paper, but you put it in wiki course, and there is one contributor, main contributor, and there is always other people as secondary contributor to this critics or these papers. And through the history of wiki course note, I can see who has done what, which contribution comes from which student, and 30% of your mark would be based on that. Again, depends on the number of students. This project could be like, we may have some mini project, like Kaggle style projects that depends on, as I said. I'm going to ask soon that how many of you are going really to take this course. Just technical detail about administrative in this course. All communication in this course would be through Piazza, and those who have been registered for the course already received an email to complete their registration on Piazza. So instead of personal email, we're going to use Piazza unless it's necessary. In final project, it's common in graduate courses. I have to mention that you cannot use part of your thesis as your final project. You can't use a project that you are doing for another course as a project here. Okay, any question about what I've said so far? Yes?
What sort of work does the group project entail?
The project is sort of open-ended. There are different type of projects that people can do. One type of project is that you have a completely new idea and you want to come up with a new algorithm. You think that you can come up with a new algorithm. So that could be a very good type of project. In this case, a negative result will not penalize you. I'm going to look at your approach and your steps that you are taking make sense or doesn't make sense. So if it turn out that your ultimate model that you are making doesn't work at all or is the worst model ever, so you're not going to lose mark as long as you have done something sensible during the term to make this model. That's one type of project. Another type of project is that you're not creating a new model, but you're using existing models, but you're applying this model to your research area or an application. This could be your research area, could be a general application, it could be a result that has been reported in another paper and it's important, interesting, and you want to regenerate that. That could be also a project in this course. When it's application, it's pretty important not to choose something which is trivial. You can't choose, for example, digit recognition as application of deep network, for example, because it's, in one afternoon you can implement it and get 98% accuracy. So it should be something challenging that let you to learn something. Also could be a Kaggle style project. There are challenges posted on Kaggle that you can choose one of those challenges. In fact, there is a project now on Kaggle, which in terms of the time fits actually our course. It has been posted 28th of August and the deadline is 6th of January. It's a classification problem. There are images and you basically need to detect right whales in those images. It's quite challenging problem, even as a person it's pretty hard to recognize which one is which. I was not able to recognize them correctly, to label them correctly. So it's a very challenging problem. There's another problem on Kaggle about rainfall. There's another one about crime prediction. Recently, all emails of Hillary Clinton was released on Kaggle just 2 days ago. Her personal email that was controversial. So there are challenges and data sets there. So you can choose a Kaggle style project. That would be also a pretty good project for this course. Yes?
So what's the difference between the project applying something to your research area and having it not be part of your thesis? Because it cannot be part of your thesis, right?
No, it not I don't mean that you cannot include this in your thesis. You can include it in your thesis. What I meant was that you can't report something that you have already done in your thesis as your project.
Okay.
But it doesn't matter that you do something which is related to your research area and then you include it in your thesis. That's fine. Yes?
Do you have any specific preference for this course, or just like papers?
It would be mainly papers. There is a, the draft of one book is online by Yeshua Bengio. The draft of the book, but it's not complete. I mean, if you look at the book in many cases, in many pages, there's still, the sign that needs to be done. It's very, early drafts of a book. I don't know any good book that we can use as a reference. So it mainly would be based on papers. This area actually moving quite fast. This book, and there is a very good book in machine learning by Morphy. It was published, I think, in 2012 or 13. It's quite a new book. There's one chapter about deep network, and if you look at that chapter, it's quite old now, after 2 years, It's because the area moving so fast. So we better use papers, actually. But I'm going to post a long list of papers that you can choose from for presentation. Okay, any other question? Okay, maybe I just ask you, how many of you plan to take the course as credit? Just I want to have some sort of a statistic. Okay. Okay. Can I borrow one of your papers? So now I have a rough idea, but that would help if you just, using this paper, I'm going to collect it at the end of the class. Just write your name, and in front of that, just tell me that you're going to register in this course, audit the course, just sitting in the course, or you're not going to show up next lecture. In that case, you don't need to write your name. But otherwise, that would help. Yes?
So what is the requirement for auditing the course?
Presenting papers, not project. Okay?
And paper critiques also for the audit, or just presenting the paper?
Just presenting papers. But part of presentation, I have to give you the detail. Part of presentation depends on Wiki course notes, so you have to write something really there. Yes?
Do we need any prerequisite, like neural network?
You are all grad students in related areas, so I expect that you have some knowledge of machine learning, and you have knowledge of calculus and linear algebra and statistics and probability. So I can't point out a single course that I said that you have to pass, you have to know this course before, but definitely I'm not going to go through all concepts of machine learning in this course. I assume that the general concepts of machine learning. I assume that you have knowledge of linear algebra and so on. Okay, any other question? Yes?
How in-depth with the actual mathematics and are you going to go with neural nets? Are you going to sort of, it's going to be like a high-level conceptual thing, or are you like, here's the equation, it works, or are you going to kind of derive why they're...
Well, actually, I think you can get a sense of this in the second half of this lecture, because I'm going to start, teaching like feed-forward neural networks. And I'm going to talk about backpropagation. You're going to get a sense that I prefer to go through details of algorithm rather than just talking about the big level. I prefer to cover fewer number of algorithms in depth rather than many algorithms just in high level. This is general. Okay. So a little bit of history of deep network. So the first attempt to make a neuron, this still, it's pretty controversial that neural network or deep network is a model of brain or is not a model of brain. I don't know. Personally, I don't believe that it's a model of brain. I think it's quite different from us, You can teach a kid difference between table and chair with one example. So this is chair, this is table. With one example, they learn. You can teach them the difference between digit 2 and 3 with one example. But when you want to teach neural network or deep network, this difference, you need 1 million examples. So I really don't think, don't see really a reason that we believe that it's a model of brain. Maybe a very simple model. I don't know. I don't know much about biology to judge this. But anyway, it's quite controversial. But the story starts from attempt of some researchers to mimic brain and to mimic neuron. So how we can make a neuron. So the first attempt was in 1943. It's also interesting to know the area of people who have been contributing in this. So in psychology, in logic, not just computer scientists and statisticians. So they basically made a neuron at that time in 1943. What they made is what we call it today logical gates, or logical circuit. So basically what they made as neuron is and or not. It's an electronic device which can simulate one of these logical operations. That was 1943. So the next attempt to make neuron was in 1958 by Rosenblatt, who invented perceptron. Perceptron is not logical gate. It basically is simply, when you have a data point, it's gonna find a weighted sum of each feature or each variable of this data point. So you're going to find a weighted sum. These are weights, will be multiplied. And then you are going to apply sine function to this weighted sum. Okay? So basically, if the result of this weighted sum is negative, after applying the sine function, it's going to be -1. Otherwise, it's going to be +1. So they wanted to use this as a classifier. Assume that you have two classes, and classes have been labeled by negative and positive. This perceptron was supposed to do this classification, so map points either to this class or that class. So when perceptron was invented, it was not quite clear that what perceptron does, the way that we understand it now, it was not clear at that time. So they didn't know that it's a linear classifier. It was a general belief that, they invented, they solved artificial intelligence. So at that time, even we didn't know how to train perceptron, The many first attempts using perceptron was just random choice for weights, until it works. It took a while until we understood how we can train them. But this is, from New York Times in 1958, based on an interview with Rosenblatt, that the belief was that they created embryo of electronic computer that expected will be able to walk, talk, see, write, and even reproduce itself and be conscious of its existence. It was the belief that they solved artificial intelligence, and the perceptron is basically what it's supposed to do. So there was big dreams about perceptron in many news that it's going to happen soon, this type of robots, this type of machines, and so on and so forth. So 1958 until 19... okay, that was in 1958. So if you compare these two types of attempts for making perceptrons, the first attempt, according to some biologists, is closer to what's happening in real neurons in the brain. But neural network is based on the second attempt, is based on perceptron. It's not based on logical gates. It's based on perceptron. So perceptron is building blocks of neural network, or also deep network. So it was 1958, as I told you, that it was invented. But it was in 1960, 2 years later, that some researchers showed how to train perceptrons in a way which is more precise rather than setting weights randomly. So this dream that perceptrons solve artificial intelligence was a common belief from 1958 until 1969. In 1969, a book was published. The name of the book is Perceptron, and this book shattered the whole dream. Basically, they showed that perceptron is just a linear classifier. It was quite surprising when they showed that perceptron cannot solve XOR problem. I mean, if you have a problem such that, there is one class like this and another class like this, it's called XOR problem. So they was very surprised that perceptron cannot do this problem because they were not aware that it's just a linear classifier. So yeah, by one line you can't make separation here. So so that was quite influential book. But this book had some sort of, propagate some sort of misconceptions of the book as well. Some people, even you can see it in many papers now, claim that this book and this researchers showed that even different layers, multi-layers of perceptron cannot solve this problem. It's not in that book, This book doesn't claim so. But it became a common belief that even with multi-layers of perceptron, you can't do this, okay? So it changed the perception toward perceptron quite significantly, this book. Still, many researchers tried to use multi-layers of perceptron, but it was not clear how to train multi-layers. So by that time, we knew how to train perceptron, but it was not clear how to train multi-layers of perceptron, how we can adjust weights in an efficient and systematic way. In starting 1969, many people invented and reinvented again backpropagation algorithm independently. So if you look at the literature, there are many people who claim that they did backpropagation, and they are right, but they did it like independent from each other in different years. Even, besides the claims that are quite popular, there are claims that it was in the literature in Russia way before that. There's a claim that it was in French literature right before this. But anyway, starting 1969, many people invented and reinvented backpropagation, and started to apply backpropagation to multi-layer perceptrons, which is also called neural network. And it was quite successful in many applications, so neural network became quite important in 1980s. Up to 1980s, it was quite successful until the time that I told you, after invention of support vector machine and some other techniques, neural network was not favored model anymore. There were many reasons for that. Neural network, we're going to see soon, doesn't have convex objective function and we use gradient descent to train neural networks. So it's quite possible that you get stuck in local mean when you are training neural networks. So that was, an issue at that time. The other problem was that we didn't know how to train networks with many layers. And why it was problematic, if you have multi-layer perceptron, or if you have neural network, you can increase the flexibility of the model by increasing the number of nodes in one layer. We can add many nodes in one layer, and you can increase the, turn it on. You can increase the flexibility or capacity of your model. And there is a theorem, those who are familiar with the history of neural network, there's a theorem which proves neural network is a universal function, means it can fit any model. But if you look at the detail, of that proof, it basically means that using neural network can overfit anything. It doesn't mean. So in this sense, lookup table is also a universal function. You can learn your training data perfectly, but you can't generalize. To generalize, you need to have many layers, not many nodes in one layer. But it was not clear how to train networks with many layers. That was one of the reasons. Another reason was that at that time, we didn't have enough data to avoid overfitting. The amount of data was limited. We didn't have the right computational power. In one of the talks, Jeffrey Hinton says that there was a historical mistake, that neural network was invented before support vector machine. So it was invented at a time that we didn't have right computational power and we didn't have enough data for that. It should have come later. Now we can avoid overfitting because we have models of millions of parameters, but we have record of hundreds of millions data, and we have GPUs, we have right computational power. So it is starting 2006, it became popular again. Even if you look at the 2006 paper by Hinton, Hinton in that paper tried to train the model in an unsupervised manner using restricted Boltzmann machine, and mentions that there are 3 disadvantages or 3 limitations of backpropagation that made him to invent, a new techniques for training deep networks. And according to him, these are 3 main limitations: that it requires labels training data, which doesn't exist. So you have unlabeled data as much as you want, but you don't have much labeled data. Go to internet, there are many images, but there is no label for them. You want to make distinction between apple and orange, there are only a few number of them that have been right labels. So backpropagation needs labeled training data. So it says that it's very slow with multiple layers, and it can converge to poor local minima. These 3 main disadvantages that he mentions in his 2006 work. Maybe only the first limitation is valid now, that backpropagation needs label training data. And it's true that most success stories that we have heard about deep network is about supervised learning. In unsupervised cases, we didn't have much success using deep network. Being slow is not a big issue anymore because we can use GPUs now, and it's 100 times faster than before, for example. And the fact that it can converge to poor local minima, it became clear that in very high dimensional space, it's not a big issue. You can go to a local minima, and all local minimas you can argue to even theoretically that many good local minimas exist, and converging to one of these local minimas would be sufficient enough. Okay. So, so in the next half of the lecture, I'm going to start really teaching the course. I'm going to start by perceptron and then backpropagation and feed-forward neural network. So between these two, we are going to take a 10-15 minutes break, and then we'll back and continue the lecture. Let me warn you that if you have seen perceptron, it's going to be just perceptron, and backpropagation next lecture. So it may bore some of you that have seen the detail of this algorithm. So I'm going to go through the detail of backpropagation, how it works, and derive all of this formula. So if you have seen this, I may bore you, but I want to make sure in the first lecture that we are all in the same page. So let's be here by 3:15.